we just mentioned that the problem with BCNF is that it gets rid of all the redundancies, but now there are some functional dependencies which are not preserved in any one table. So 3NF is pretty similar to BCNF, but the rule just has one extension. A relation R is in 3NF if X determines P is a non-trivial dependency in R, then X is a superkey for R. So that part is still the same as BCNF. Or P is a part of a key. That's the part where we're adding in 3NF. Okay, so P is a part of a key. Note that this key is minimal, because if you're talking about superkey, then any attribute could be a part of a superkey. And also it says a key rather than the primary key. So as long as you can find a minimal key where B is part of that, then that could be excluded. Let's see an example. So the one that we were just talking about, is this in BCNF? This is not in BCNF because unit is not a superkey for this relationship. Unit can only find company and not product. Unit is not a superkey, so this is not in BCNF. Then we need to find the keys. Company and product together have the closure of those two give you unit, so this two together is a key. Unit gives you company, so unit and product together are also a key. Right? So first I need to find all of the keys, which is not an easy thing to do by any means. You find all the keys, and now you ask yourself, is company part of any key? And company is part of a key. Since company is part of a key, that means that although this unit is not a superkey, but the second part of this sentence is true, so this is going to be in 3NF. Right, so let me just go over that once more. 3NF is similar to BCNF with one additional rule. And the rule says that if you have a rule which says X determines B, and although this B is not, and although X is not a superkey, if B is part of a key, then this is fine. Okay, so this unit determines company is violating BCNF. However, it's not violating 3NF because company is part of a key, a minimal key. Any questions? Now, to be able to decompose into 3NF, we're going to rely on minimal cover. Question? Charles? Is it?
Yeah. If B is a key, doesn't it tell you that X is a superkey?
The question is, if B is a key, doesn't that mean that X is a superkey? Let's look at this. B is part of a key, company, but unit is not a superkey.
Is it not?
So unit gives you company, but it doesn't give you product. Right? So the closure of unit only has unit and company. And it does not have product. So unit on its own cannot be a superkey, right? Because unit, if you find the closure of that, you get unit. And based on the first rule, you're also going to get company. You get anything else? So it's not a key. It's not a superkey. Right? So it's not a superkey, but given that this is part of a key, then it's fine. Okay, so let's see what we mean by minimal cover. The goal of minimal cover is to transform the current functional dependencies that we have to have them as short as possible and to have as little as possible. Okay? So minimal cover is looking for G for a set of functional dependencies where the closure of the functional dependencies that you have in G is similar to F. the right-hand side of each functional dependency in G is a single attribute. Right-hand side, you want everything to be a single attribute. And you want it to be the case that if you delete a functional dependency in G, or delete an attribute from a functional dependency in G, the closure changes. That's what we mean by minimal, right? There's not a single thing that I can take out and maintain the same closure for everything. So intuitively, based on this, every functional dependency in G is as small as possible, and we get rid of all the redundant functional dependencies as well. So, as an example, let's go through an example. So when you're finding minimal cover, there's going to be 3 golden rules that you need to go through. First rule says that you need to put all functional dependencies in standard form so they would have one attribute on the right-hand side. Okay, so let's have this as a running example. This first FD has one thing on the right-hand side. This is fine, this is fine, this is fine. This is not fine, so I'm going to replace this functional dependency with these two. This is fine because we looked at the different rules that you have, and decomposition was one of the rules which were sound and approved, and it was always fine to take a rule and decompose it into 2, like we have here. So we had decomposition and we also had union, and both of those are fine. Okay, so that's the first step. Second step means you need to go through each of the left-hand sides and make sure that they are minimized. Okay, so let's take the highlighted functional dependency as an example. That functional dependency says that A, B, C, D determines E. Okay, so if I find the closure of A, B, C, D, I get A, B, C, D, and based on the highlighted rule, I'm also going to get E. Do I get anything else? I don't get anything else. Now, what happens if I remove B from this rule? If I want to find the closure of ACD, then you can see that that first rule says A determines B. So first of all, I get ACD. Since I have A, I'm also going to get B. Since now I have A, B, C, D, I can also get E with the highlighted rule. So I took out this B, and I didn't really lose anything. Right? So the second step, you're going to go through each of the rules and you're going to minimize them. Now this one was pretty obvious, so because I could see A is determining B, if I wasn't sure, then I would have had to look at ABC, ACD, I did have a look at ABE, and all the different possibilities to make sure that what I have is minimal. Any questions? Third rule says that go over the rules and see whether anyone is redundant or not. Now, how am I going to check if something is redundant or not? If I want to consider a rule to see whether it's redundant or not, let's try ACDF determines E, the first highlighted rule. If I want to see whether this is redundant or not, what I'm going to do is I'm going to find the closure of this without considering that rule. Right? So I'm going to see what is the closure of ACDF, and I'm going to ignore that rule to see whether I can get it based on the other rules that I have. So this rule I'm currently ignoring, and if I know ACD, I can already get E based on the second rule. So I have ACDF, and the second rule tells me if I have AC and D, I can get E. So since I can get the same closure without considering this rule, then I'm going to drop this rule. I don't really need it. And I'm going to do the same thing with ACDF. Make sure you're not dropping rules, multiple rules at the same time. Right? So drop that one. Then consider another one. That means now you're going to ignore it. Try to find ACDF. Try to find whether you can get to G. If you can get to G, then you can get rid of that. The closure of this is actually bigger, but all I care about here was whether I can get E or not, so I can drop that rule. So then the final answer will have shorter rules. Now I dropped B here, and I will have less rules. This would be minimal cover if and only if there's not anything I can drop from the left-hand side anymore to have the same closures, and there's not a rule that I can omit anymore to get the same closure. Right, so why don't you do this one? So the projector on the left has a previous example for your consideration. Anyone lost? Not sure how to do that?
Whether that so you want to drop the rules, you want to drop them. So what's the current closure of if you have that, right? What would be the closure
Everything's set up for C goes to everything.
Because you're dropping down. So, yeah, so defining the closure of JP with that, what if the closure of JP without the same? Because that's the one I want to on the right, so since the closure G, that we cannot, we don't need that.
Maybe Jake's has to.
The redundancy is one.
Right, let's look at it together. Okay, so these are the golden rules again. First one says, put all FDs in standard form. So I need to take that big ugly functional dependency at the beginning, and I'm going to convert it into a bunch of small functional dependencies. So C now gives me S, C gives me J, C gives me D, C gives me P, C gives me Q, and C gives me P. JP gives me C, SDP, and J gives me S. So everything on the right hand side now has one value. So I'm done with the first step. Second step says, can I shorten any of the FDs? So if I want to do that, I have two FDs where there are multiple values on the left hand side. JP is one of them, right? So the question is, can I make that shorter to make it either J or either P? And what I'm going to do is, I'm going to find the closure of JP. What's the closure of JP? So JP gives me C, and C gives me everything else.
Fire status has been updated.
Thanks for the update. Okay, so now if I want to be able to make that shorter, I have to see whether if I change that rule, I can get the same dependencies or not, right? So let's look at closure of J. So if I look at closure of J, does J give me anything? J. What else? S. What else? Nothing. So with changing that, I cannot get the same closure. So I cannot make that any smaller. So for step 2, I can't really make anything smaller. So what I'm going to do is, I'm going to check to see whether I can remove any FDs. Now I'm going to consider C determining S. If I want to consider removing this, what I'm going to do is I'm going to ignore this rule and see if I can get this without having this rule in place. Right? So what I need to do is to find the closure of C without considering this. And then I need to do it with considering this. And to see whether I get the same values or not. The closure of C is going to give me CJDPQVS. And if I don't consider that and I do the closure again, I'm going to get the same value. Where am I going to get S from? I'm going to get S from J, from the last one. Since I already know J, J is going to give me S. So I can remove that rule and I'm still safe. Can I get rid of C determining P? If I remove that rule, then since I already know S and D, based on S and D I can still get P. So I can remove these two rules to get a minimal cover. Minimal cover is not unique, right? So you can get a different minimal cover depending on the order of things that you omit and order of rules that you shorten first. However, as long as you have a minimal cover which satisfies the rule that you can't make any of the rules shorter and you can't omit any more rules to get the same closures, you're in good shape. Any questions? Okay, bad stuff will happen if you change the order of the rules that we have. So the rule says put in standard form, minimize, delete. If you put in standard form, delete and then minimize, you're not going to end up with minimal cover. Okay, so make sure that you keep with the order that we have, and don't start with removing redundant rules and then moving over to see whether you can make anything shorter. Let's see an example. So A, B, C, D gives you E, E gives you D, A gives you B, and AC gives you D. If you look for redundant rules, none of the current rules are redundant. Right? So that means you cannot take away any of those rules and get the same closures for everything. Okay, so now we're done with this step. Now you move to step 3. If you now move to step 3, you can take this rule and you can shorten it to AC giving you E. Why can you do that? Because you can omit B because A gives you B. And if you have A and C, that gives you D. So based on these two rules, you can shorten this to have AC gives you E. You've done all of the steps, so you should end up with what is now minimized, a minimal cover. However, that is not the case, because now if you look at this, this rule can be deleted and you'll still keep all the closures. Alright, so just a word of wording that the order of the ways that you do the steps matter when you're finding minimal cover. Any questions? Okay, so let's see how we can decompose into into 3NF. So what we're going to do is we're going to have the functional dependencies that we had like before, and at each step, now we're going to check whether a current table is in 3NF or not. If it's in 3NF, that's fine, it's all good. If it's not, we need to decompose it based on the rule that we had at BCNF. So it's the same rule, you have X and B, now you're going to put X and B into one table and you're going to put everything else in another place. Before you begin though, it's important to start with a minimal cover set. This was not something that you needed for BCNF. However, for 3NF, it's important to start by putting the functional dependencies that you have in minimal cover. At the end, when you have decomposed everything down, now we're going to check to make sure that all the dependencies are being preserved. So if I have a rule which says AC gives you B, then after I'm done, I'm going to make sure that this rule shows in one of my tables. if I currently don't have a table which has all three of these attributes in it, I'm going to add a new relation, or n, depending on what I'm at currently, and I'm going to add a, c, and b as a relation as well. Okay, so pretty similar to BCNF. All your knowledge is still valuable, don't worry. First of all, you need to find minimal cover though. And at the end, you need to check to see all of the dependencies are being preserved. If they're not, we're going to add back some relations in order to take care of those. Okay, let's do an example. So A, B, C, D, E, and let's say we have two functional dependencies. A, B gives you C, and C gives you D. If you check, this is already minimal cover, so we don't need to make any changes with that. One thing which we need to do with 3NF that we weren't doing before is finding the minimal keys. When we were dealing with BCNF, all we cared about was whether the thing that we have on the left-hand side is a super key for our current relation or not. However, with 3NF, you need to know all of the keys. So if you have a rule, if this is not a super key, now you need to check to see whether this B is part of a minimal key or not. To check that, you need to find all the minimal keys. Right? So for this relation, what I'm going to do first is, I'm going to find all the minimal keys. If I have AB gives me C, C gives me D, so AB gives me A, B, C, D, there's no way I can get E, so E needs to be part of the key as well. So A, B, E, the closure of that gives you everything, and that is the only key for my relation. Again, actually finding just the minimal keys for a relationship is NP complete. Okay, so unfortunately there's no easy algorithm that I can give you to find all of the minimal keys. However, based on the smaller examples that we're doing, if you just go through the functional dependencies, you should be able, and using closures, you should be able to find the minimal keys. Okay, so now I know what the key is. Now I'm going to look at this functional dependency. AB determines C. First question, is AB a super key? The closure of AB is just ABC, D. It doesn't have E in it. So it's not in BCNF and it's not a super key. The next question is, well, is it at least the case that C is part of my key? The attribute C is not part of a key, therefore this is not a 3NF. It's violating 3NF, so I need to decompose. Alright, so once more, the two things I'm going to check is first to see whether AB is a super key, because if that's a super key then I'm in good shape, that's fine. If it's not, I have to check the second condition to see if the thing on the right hand side is part of a key. C is not part of a key, so this is not a 3NF, so I need to decompose. How I decompose is similar to how I was doing it in BCNF. So ABC is now going to be my R1, and ABDE is going to be my R2. Again, if you look at here, you can see that AB gives you C and C gives you D. With transitivity, you can see that also AB determines D. You could also see that by finding the closure of A and B. Right? The closure of A and B, we're giving you A, B, C, and based on that final rule, it's going to give you D. So we have this implicit functional dependency that AB gives you D. Now let's see if that's violating 3NF or not. First of all, in this relation, I'm going to check whether AB is a super key. AB is not a super key because I can't get to E. So it's not a super key. Is it the case that D is part of a key? D is not part of a key, so again this is violating 3NF, so I need to decompose. I'll decompose, I'll put A, B, and D in one relation and A, B, and E in one relation. So now I have R1, R3, and R4. All these three are now in 3NF. So that's fine. Now I need to check to make sure all my functional dependencies are being preserved. A, B, C, is that being preserved? I have R1, which contains all three of these attributes. So that's being preserved, that's fine. I look at the second one, is this one being preserved? CD is not in any of my relations. That means I cannot use any of my current relations in order to find whether this functional dependency holds or not. So I'm going to add back a function, a relation R5, which now contains C and D. Right?
Is R3 really necessary?
The question is R3 really necessary? So, you would say R2 is enough? Is that?
So, like, instead of R3, couldn't you just have R5 there and be done with it?
Okay, so the question is, once I bring back R5, it might be the case that what I have is redundant, right? Sometimes that would happen. We're not going to get rid of those because there's no easy algorithm that I can tell you guys to then go back and check those. This is in normal form, third normal form. However, there are times where you can reduce the tables. But you don't need to worry about that. As long as what you have is in third normal form, we accept that as the right answer. Any questions? Okay, so since I see a lot of stares which kind of tell me that you might be confused, can you press A if you're following that and B if you want me to go over it again?
And then we added in an explicit functional to split to A to B. Then we sort of find all of the dependencies that we created.
Okay, so let's cover it one more time. Okay, so my rule says if I have x gives you b, for this to be 3NF, either x needs to be a superkey, or b is part of a key. Okay, so these are the two rules that I have. Now this is what I'm going to consider every time I'm going to look at each of these. Since this one is talking about whether B is part of a key, it's good practice for me to find all the keys first. Right? So I'm going to look at this relation and I'm going to find all the minimal keys. A, B determines C, C determines D, so the closure of A, B is giving me A, B, C, D. None of my functional dependencies allow me to get to E, right? So to get a key, I need to add in E as well. So the only key for my relation is going to be ABE. Now that I know what my key is, I can check based on these two rules to see whether something is in 3NF or not. I have a functional dependency which says AB determines C. First question, is AB a key? The closure of AB is ABCD, does not find E, so AB is not a super key. My second option would be whether B is part of a key. So the question is C part of a key? This is my only key, C is not a part of it, so this is violating 3NF because neither of those are valid. Since it's violating, I'm going to decompose it similarly to how I was doing it before. So I'm going to put ABC in one relation and DEAB in another relation. Now I have two tables. Let's check ABC. Is this one in 3NF? So either of those need to be true. Is AB a key for this relation R1? AB is a key for this relation, so this is fine and it's in 3NF. I don't need to worry about it. If you look at ABDE, I have a functional dependency which says C determines D. Is C a key, a super key for R4? The closure of C is what? CD? It's not a key because I can't get to A and B. So I have to check the second thing. Is the right-hand side, D, part of a key? It's not. That means then R2 is violating 3NF. I decompose like I was doing before. ABD is going to be in one table and AB is going to be in the second table. Now I have three different tables and all of these are in 3NF. None of these are violating 3NF. The last question I'm going to ask is, are all my functional dependencies being preserved? So I want it to be the case that I have at least one table that allows me to check each of those functional dependencies. I have R1, which allows me to check the first functional dependency, A, B determines C, but I don't have a table which has both C and D. Since I don't have such a table, I'm going to introduce R5 as a table to be, so I can preserve this functional dependency in one table. Any questions? Well, the best way to learn is by examples. So let's do an example. Okay, and again on the left-hand side you see the example we just put together. Feel free to discuss this one over with your neighbors.
It's just the original table take away the right.
I guess so. Where would you get D though?
No, but you have to use the key.
To start.
The key should give you everything you need.
I'm using it a different way to do it.
Wait, it does?
Same examples.
Wait, oh, so are we using that? Because it only gives us those three possibilities.
Right.
So use the other one.
So you need at least 4 letters. Oh, okay, and I thought 4 letters, so
Well, maybe we are supposed to, because I can figure out what to do with this one. Are we only using those? Yeah. Or are we relying on the one from the other?
Oh, no, just
and you can't remember. So now that you have the key, what you need is to
Does anyone need more time? Right, quick when you're done.
I'm just taking. Are you just trying?
Oh, I worked on that. It's the base library. You would just
Oh, you did this one.
normal reservation.
I'm gonna use your C as well. And it's a C J.
together. Okay, so first thing I'm going to check is to see whether it's minimal cover or not. And this is already minimal cover, there's nothing that I can reduce. Okay, so then let's find some closures. Closure of JP is JP and S. Closure of SD is SD and P. And closure of J is just JS. What's my key? My key would be JDQV. Right? Because if I find the closure of JDQV, I can find everything. Yeah, Charles.
The closure of JP is yes.
So the question is, JP doesn't the closure contain C? And it does. Thank you. Okay, so now let's move on. Let's have that information up here. Now let's check SD determining P to see whether that violates 3NF or not. So SD is not a key, it's not a super key, and P is not part of a key. So SD determining P violates 3NF. So I'm going to decompose based on this functional dependency. SD and P is going to be in one, and everything else is going to be in another relation. Okay, so this one is now fine because SD determines P, so SD is a super key. In R2, I have J determines S. What's the closure of J? It's just JS, so it's not a key, it's not a super key. And S is not part of a key. Okay, so S is not part of a key, J is not a super key, so this is violating 3NF. Let's decompose further. And we'll have JS in one relation and CJDQV in another relation. Now let's see if R4 is violating anything. So does JP determine C hold here? J is not part of this, so this doesn't hold. SD determining P, P is not here, so that one doesn't hold. J determines S is not here. Let me check the closures. The closures doesn't show any violations neither. Okay, so no more violations. Then I have to check if all the FDs are preserved or not. So let's check all the FDs to make sure that they are preserved. And I can see that I don't have any tables which currently allows me to preserve JP determines C. Okay, so I need to add R5 back in so I can preserve this functional dependency as well. So the final answer is going to be R1, R3, R4, and R5. Yeah.
At the start, does JP and C violate 3NF?
At the start, does JP giving you C violate CNF? Well, JP is not a key, and C is not part of your key, so yeah, it is violated. CNF. So if you started with that, you would get a different answer probably to this one.
And would that answer be right?
Yeah, definitely. So if your answer looks different to this, that doesn't mean it's wrong. Right? There are, depending on the order in which you go through the violating functional dependencies, might give you different answers. Again, at the end, one way that you can make sure that what you have is correct, one is to validate all of these. Check all of these to make sure that none of them are violating 3NF, and also make sure that you're always preserving all the dependencies if this is in 3NF. Any questions? Okay, one final exercise for today. Feel free to discuss it with your neighbors.
Then you have to check the right hand side to see if that's part of the key.
Great. So Let's start by finding some closures, right? So ACD closure would be ABCD. AC. What's the closure? ABCD. D. What's the closure? DC. And AC we've already done. Okay, so this is a key. Do we have any other keys? What?
AD.
What's that?
AD.
AD. What's the closure of AD? D gives you C, AC gives you C, and AC gives you B. So keys, AC, and also AD. So you need all this information before you start. Now let's look at the first one. R is neither in BCNF or in 3NF. So let's see whether it's in BCNF first. ACD determines B. ACD is a super key, so that's fine. AC determines D. AC is a super key, that's fine. D determines C. D determines C. D is not a key. So this is not in BCNF. Right? So since it's not in BCNF, it cannot be D and it cannot be B. It's either A or C. The question is it in 3NF? Now, for this to be in 3NF, we need to go back to here, to this D gives you C, and see whether it would be in 3NF. D gives you C, D is not a super key, however I have a key in which C is an attribute. Since C is part of one of my keys, then D giving you C is not violating 3NF. And finally, AC gives you B. AC is the super key, so that's also fine. I look at my closures to see if there are any other dependencies that I'm missing. There aren't any other things that I'm missing, so C would be the right answer. Which the majority is taken. So I know that this stuff is pretty hard, and it needs practice. We're gonna have a tutorial next week before the midterm for you guys to practice this. You know, do go back to the questions that we've done together and make sure that you cover them. Let's compare BCNF and 3NF. Not yet. I believe soon, but let's compare BCNF. So BCNF guarantees and removes all the redundancies. 3NF brings back some redundancies, but allows you to capture all the dependencies that are being preserved. Okay? If a relation is in BCNF, it's also in 3NF. So this is what all the normal forms look like. Everything is in 1NF, then 2NF, then 3NF, and then BCNF is the smallest here. So if you knew this already, then you would have known that anything is in 3NF is also in BCNF, right? So you can't have something which is in 3NF but not in BCNF. However, you can have things which are in 3NF but are not in BCNF, so they're going to lie somewhere around here. Most organizations go with something with 3NF or BCNF, depending on the sort of dependencies that they have, and whether the functional dependencies, how important they are, and what are the size of the tables that they're storing them in. Okay? Because now it's a trade-off, right? So now you should either go for a bit of redundancy, or you're going for a bit of making sure that all the dependencies are being preserved. sometimes, although that you know what normalizations look like, some companies or enterprises denormalize some of the things that they have because of the rules that they have in their databases, right? So you might have rules that you might want to have fewer joins because of the kind of queries you want to find. So although that normalization is usually the best answer, once you have knowledge of it, it might be the case that you need to go back and denormalize some of the tables that you have in order to answer some queries more efficiently. The learning goals that you make sure that you know for this chapter, this is chapter 19, is debate the pros and cons of redundancy in a database. Now you know some of the pros of redundancy. Because up to now, we always said we don't want redundancy. Let's get rid of redundancy. But sometimes we actually introduce it back in because of BCNF. Provide examples of update, insertion, and deletion anomalies. We covered quite a bit of those. Given a set of tables and a set of functional dependencies, determine all the keys. So make sure that you're comfortable with finding minimal keys and also super keys. Show that a table is or isn't in BCNF or BCNF. Prove or disapprove that a given decomposition is lossless. So if you have a loss, if you don't use BCNF and you're just randomly putting values, you might get loss lead decompositions. And also be able to decompose table into set of tables. Any questions? Question?
Yeah, it's for the. Can you go back to the critical question?
Yes.
For the AC determines B, but B is also not in the key, so for that to say.
AC determines B,
Yeah, but B is not in the key.
but AC is a super key for that table. Right? So since AC determines everything, so AC is a super key. Good question. Question?
What is the midterm cutoff for this material?
The midterm cutoff is going to be chapter, so everything we've done up to here, and also chapter 4, which is, we're going to cover on Monday. Okay, so chapter 1, 2, 3, 4, and 19. Any other questions? Have a great weekend.